Hi, this is Tzvi Rosen. Today we're going to be discussing fractions and localization. This corresponds to Chapter 3 in Atiya McDonald. We'll start by defining rings of fractions and exploring some of their properties. Then we'll look at localization, which is the process of constructing a ring of fractions as a functor from one category of modules to another. And then we'll look at local properties, which are properties of rings and modules that you can check at localizations at prime ideals. Okay, so we'll go through all of these topics. Let's start. So we're going to define rings of fractions and or localizations first in the case of an integral domain. Okay, and the guiding example that you might want to keep in the back of your head is how we can take the ring of integers and construct rational numbers. Okay? So we'll start by defining a multiplicatively closed subset, also called a multiplicative set. Okay, so we'll take a ring A. We say that a set S contained in A is multiplicatively closed if we have the unit, the multiplicative unit, 1 is in S, and the set is closed under multiplication. So x and y in S implies xy is in S. Okay? So we're going to define next the localization of A at S. Alternatively, the ring of fractions with denominators in S as the set of fractions with denominators in S, A over S where A is in A and S is in S. Okay, and so we're saying this is a ring, so we need to have ring operations. So we have to have addition and multiplication. Well, if we take A1 over S plus A2 over S, this is going A1 over S1 plus A2 over S2. This is going to be equal to A1 S2 plus A2 S1 over S1 S2. Okay. So clearly this is this is still in the ring of fractions with denominators in S based on the property of multiplicative closure. So the fact that this is multiplicatively closed means this is in S. Okay, and obviously the top part is in A. Okay, so this makes sense. And similarly, you have multiplication A1 over S1 times A2 over S2 equals A1 A2 over S1 S2, and the same points hold. This is in A, and this is in S. Okay. So we defined this set of A over S, but one thing we didn't take care about is what if we can cancel things in the numerator and the denominator? How can I tell that two fractions are the same after cancellations? And we'll define that in the standard way using cross multiplication. So we want to mod out modulo the equivalence relation a over s will be equivalent to b over t if, when you cross multiply, you get the same thing. If at is congruent to bs, I'm going to write it as a subtraction for reasons we'll see later. Okay. And so this defines our ring of fractions with denominators in s, or the localization at s. Okay, now let's see some examples with the integers. As we mentioned, you can form the rationals out of the integers with this process. So let's show how. So if you set your multiplicatively closed subset to be the integers except 0, then clearly 1 is in the subset, so that's good. And also it's multiplicatively closed because any product of integers which are each not 0 is not 0. So this is multiplicatively closed. And by localizing at s, you obtain the field of rational numbers. Okay? Right? Because you have any integer in the numerator and any non-zero integer in the denominator. But this is not the only multiplicatively closed subset that you can take in the ring of integers. Another one you could take is basically the set of powers of any integer. Okay, so let's say it's n to the k, where k is greater than or equal to 0. Okay, you include the 0 there to make sure that 1 is in your multiplicatively closed subset. So let's take as an example 12. Okay, so that's actually a little too big. Let's do 6. Okay, so then for n equals 6, multiplicatively closed subset will be 1, 6, 36, 216. My apologies if my arithmetic is wrong. When we want to look at S inverse of z, the localization of z at s, this will look like the set of fractions of the form a over 6 to the k, where a is any integer and k is a positive integer, a non-negative integer. Okay, so you might look at this and kind of get a little bothered by the fact that you could have, we're demanding powers of 6 in the denominator. So let's mark this specifically. We have powers of 6 in the denominator, but what if we had something like 2 in the numerator? So we could say 2 over 6. Well, then this is going to be equal to 1 over 3, right? We can cancel. So I'm going to tell you not to do that, right? Don't do any cancellation. That doesn't make sense for your multiplicative subset, right? And once you avoid canceling things that you shouldn't be canceling, this is fine. So only cancel when it makes sense. Okay. So one more example of a multiplicatively closed subset of the integers is the complement of a prime ideal. So let's take, this will be z, leaving out the ideal generated by some prime p. Okay. So for example, if p equals 2, then we're looking at s being the odd numbers. Okay. And so when we when we want to localize at S, what we get is the set of A over B, where A is an integer and B is an integer which doesn't divide P, or which P doesn't divide. It's not divisible by P. So B in Z, and P does not divide B. Okay, so in this example, this would just be the fractions with odd denominators. Okay, and you can convince yourself that multiplication and addition respects these operations. I mean, we already proved it just by the formula, but kind of do some mental math, and you'll see that multiplication and addition always of fractions with odd denominators always gives you odd denominators. So, so this is another example of a localization of a ring. Now let's look at localizations of a different ring. So let's say we're looking at k adjoin x. Okay, so this is a polynomial ring, coefficients in k. So the standard thing to do would be in the same way that we localized by the whole ring of integers except for 0, you could do the same thing here. So if we let S be equal to k adjoin x except 0, then what we're looking at, so clearly this is a multiplicatively closed subset. When we look at S inverse, we'll put this over here, k adjoin x, this is going to be the field of rational functions. This is, which is often denoted with a round parentheses. Okay, and that's simply because this is the set of f of x over g of x, both polynomials, right? And g not equal to 0. Okay, so that's one example of a localization of k adjoin x. Another example would be if we take powers of some, the same way we had powers of some integer, we can take powers of some polynomial. So we could take this set. So this will be, if we try to localize here, so and S inverse k adjoin x, this is going to be the ring of what's often called the Laurent polynomial ring in one variable. So this is the Laurent polynomial ring. Because we're allowing a few negative powers of x as well. And I'll just remember to write up here rational functions. Okay. So this is another localization of k adjoin x. And just as we had with the integers, we can also do with the ring of polynomials, we can take the complement of a prime ideal. Obviously, the prime ideals here, besides 0, which we already discussed, are the maximal ideals. So let's take, the complement of some maximal ideal. The easiest one to do is just the ideal generated by x. So we can take S to be k adjoin x, except for the ideal generated by x. Okay, well, what does this look like? So S inverse k adjoin x will be the set of fractions where You have f of x over g of x. And here, g of x cannot be a multiple of x. If we're thinking of these not as polynomials per se, like an algebraic object, but as functions, what this means is that this function will be reasonable at 0, right? You'll be able to compute the value of this function at 0. So we could think about this as rational functions that are well behaved at 0. Okay, so not the rational functions that have poles, for instance. So 1 over x will not be in this localization. Okay, so that gives us a flavor for some different localizations we can do in our favorite rings. So let's now generalize a bit. So both of those rings were integral domains, but there's a problem if we try to do this construction for non-integral domains. And here's where the problem shows up. So let A be a ring, not necessarily an integral domain. Okay, and now let's say we're going to localize at S. So we're trying to consider the set of A over S, where A is in A and S is in S. And we made this claim about this equivalence relation. So this equivalence relation, we're saying if you cross multiply and subtract and you get 0, that should mean that the fractions are equivalent. And that should be an equivalence relation. So in particular, it should have the transitive property of an equivalence relation. So the problem is, suppose we have AS and we're saying this is equivalent to B over T in this equivalence relation. Then we have B over T is going to be equivalent to C over U. Okay, so what would that mean? So we would have AT minus BS is equal to 0 in this ring, and BU minus CT is equal to 0. But now we have a problem because I can't combine these these identities, these equations in a meaningful way without adding in some constant. So if I multiply this by U, so I get U times AT minus BS equals 0, and I multiply this by S, so I get S times BU minus CT equals 0. Now I have the bus, BSU, in both equations, and I can just add them. And I'll get ATU minus SCT, or STC. Wait, which do I want? Let's put the C first. CST equals 0, which, if I factor out the T, this is equivalent to saying T times AU minus CS equals 0, which would tell me, in much the same way as these equivalences, that A over S is equivalent to C over U, but we have this pesky T in here. Okay, so in an integral domain, I don't have to worry about T because t is non-zero, and so you can cancel it and find that AU is equal to that AU minus CS is 0. But if we're not an integral domain, this is a problem. So we have to adjust the equivalence relation. So instead of saying A over S is equivalent to B over T if AT minus BS equals 0, what we'll say instead is A over S is equivalent to B over T if there's an element U in S, right, in our multiplicative subset, such that AT minus BS times U equals 0. Okay? And so then the fact that we had this extra t here wouldn't bother us. It would still satisfy the definition of this equivalence relation. Okay. Another way that we could define localization is by universal property. And we know we always like to find universal properties for things. So how does this universal property work? So the localization is a special ring such that, so if we fix our A be a ring, and we have S and A a multiplicative subset, then we say that for any f from A to B, okay, we're talking ring homomorphisms here. So ring homomorphism, where B is also a ring. There will, with the property, this is the key, with the property that f of x is a unit. In other words, it's invertible in B for all x in S. Okay? So this is the property that f has. Then, so there exists a unique homomorphism, G, such that S inverse, such that the diagram here commutes. G from S inverse A to B, such that the diagram commutes. I suppose I should specify that this is kind of a fixed map here, so let's call it I. So given the way that we define the localization using the universal property is to say that it's a ring equipped with the homomorphism I mapping A to that ring, such that no matter what map I choose over here, if it sends all of these S guys to units, then it has to pass through here, and there's a unique way for it to pass through there. Okay? Hopefully that's clear. Okay. So why are we using the word localization? So the terminology comes from the fact that we have an object called a local ring. So local ring is a ring with one maximal ideal. So exactly one maximal ideal. Okay? And the reason why this is called maximal, why this is called local, you can think about in terms of geometry. So you might remember that so the maximal ideals of, let's say, C adjoin xy were of the form x minus a, y minus b. So by talking about a ring with a single maximal ideal, you're basically kind of zooming in on a point. That's maybe the intuition that you can get, right? Because the AB corresponds to a point in C2. Okay. So localization, if you take S to be the complement of a prime ideal, then the localization is a local ring. And the maximal ideal, the unique maximal ideal, is given by, is basically just it's generated by P. You need to translate it to the new ring, so it's P times S inverse A. But that is a local ring. So the notation for such a local ring for S inverse A of this type is A sub P. Okay. So this is the localization of A at P, and you do have to be careful that what we're doing here isn't localizing the prime ideal itself. We're not inverting the elements of the prime ideal itself. We're inverting everything outside the prime ideal. Okay, so the prime ideal, everything in there is still not invertible. If you were to have an invertible element there, then it would generate 1, and then you would get the whole ring. So clearly that's not going to happen. We're not inverting anything there. We're inverting everything outside. Okay, and that's why you're left with that single one maximal ideal, because everything outside is invertible now and will generate the whole ring. Okay. So let's do a quick example. So if I were to take, as before, so if I have the ring Z, so let's make A equals Z, and P will be, just the only prime ideals. There's 0, and there's the, I guess you need that, oh no, it's fine. I guess fields are strictly speaking, fields are strictly speaking local rings because their maximal ideal is 0. Okay, so P, you can either have 0 or the ideal generated by a single prime. So then let's see what these are. So localized at 0, that's the field of rational numbers, and that's why I was just saying, wait a second. But no, that's fine because its maximal ideal is 0, so it's still local. And ZP, so localized at P here, this is equal to, as we mentioned before, A over B, where P does not divide B. Okay. Let's do another quick example. So if we have CXY, okay, and that's what we mentioned on the previous page, then your primes can take a few different forms. So you can have the 0 ideal. You can have the ideal generated by a single irreducible polynomial. And you can have ideals of the form x minus a, y minus b for a, b, and C2. Okay? So just using A here, so A0, this is going to be the field of rational functions in 2 variables. So A localized at x minus a, y minus b. This will be the field of rational functions that do not have a pole at AB. So rational functions well defined at AB. As for the other one, so F irreducible, it's a bit trickier. So now you're allowed to invert everything that's not a multiple of this polynomial. So you can think about this as rational functions whose denominators are not identically 0 on the curve defined by f of x, y equals 0. Okay. So we have this local picture here. We're looking at rational functions that are defined at some subvariety, and I'm using the language of varieties, and you'll forgive me. Hopefully we'll discuss varieties in a lecture soon. But you're looking at the rational functions that are defined on most of the variety of interest. So for the prime 0, you're looking for rational functions that are defined on most of the full plane. And for this one, you need rational functions that are defined on your point. Okay, and for this, you need rational functions that are defined for most of your curve. Okay, so that's the localizations that we're looking at. Okay, now one comment about ideals of S inverse A. There's a bijection between primes of S inverse A and prime ideals, meaning, and primes of A that do not meet S. Okay, so in particular, the prime intersected with S will be the empty set. So taking, so P in S inverse A, so there's a natural homomorphism, so F from A to S inverse A, which just maps x to x over 1. So if you have a prime ideal here, then you can just take the preimage under F. So this will map to preimage of P in A. Okay? And this ideal will be prime because preimages of prime ideals are prime. How about going the other way? So while preimages are prime, the images of prime ideals are not necessarily prime. So let's consider what happens. So we're going to claim that under the same map which sends A to S inverse A, we're going to have that that P in A will map to S inverse P in S inverse A which will be prime. Okay, and by S inverse P, I just mean take the prime elements and then just multiply it by all of the inverses of the elements of S. And so the way that we might prove this is to consider the quotient of S inverse A by S inverse P. So S inverse A mod S inverse P, it's going to be equal to, or isomorphic in an obvious way, to S bar inverse of A mod P, where S bar is the image of S under the quotient. From A to A mod P. So when we're thinking about so given that we have this isomorphism, which I haven't really justified, but you'll take my word for it at this point, we're looking at a localization of an integral domain, because a quotient by a prime is an integral domain. So the localization of an integral domain is also an integral domain. And you can convince yourself that's true by thinking about where zero divisors would come from. Is also integral domain, or it's zero, right? And that would happen if you tried to invert zero, right? Because then you would just get the whole ring. Then the whole ring would just vanish, get eaten up by zero. So looking at this, if it's an integral domain, then that means that this, that means that the thing you're quotienting by, specifically S inverse P, is prime. Okay, so that's one option. The second option is that it's zero, but that implies that S inverse P is equal to the whole ring, S inverse A. But what that would mean is that S inverse, or S, has to contain an element of P. Okay, because then you would invert that, and then you would get the unit, right? Because if you have 1 in S inverse P, that means you're able to invert something in the prime ideal. So for this reason, but we know that S intersect P is empty, because we're only looking at primes that do not meet S. So that means we're left with this option, specifically that when we pass to the localization, the image of the prime is also prime. Okay, and the last thing we'll mention in this first part of the lecture is how to turn an A module into an into a module over the localization of A at S. So let's say we have a ring A, and we have S, a multiplicative subset, then, and we have a module a module M over A. We can just define M as an S inverse A module by letting, so we'll take S inverse M to be defined as M over S, where M is an M and S is an S. Okay? And here we will want to be able to add and scale things by elements of A, but that's you're still perfectly able to do that. So M1 over S1 plus M2 over S2. You can use the rules of addition from the ring and get S2 M1. Okay, and you certainly can scale module elements plus S1 M2 divided by S1 S2. So that's how you add elements of this new localized module. And in terms of scaling by A, so if you have A times M over S, well, that you do it in the standard way. You just get AM over S, and then you apply the A multiplication that M already comes with. And here you also have to be cautious about the equivalence relation that M1 over S1 is equivalent to M2 over S2 if we'll use the same condition as we did for general rings. If there exists A and S such that A times M1 S2 minus M2 S1 is equal to 0. Okay. So now S inverse M can be thought of as an A module, but it also can be thought of as an S inverse A module by just adding in this. Okay. So if we take an element in the localization in S inverse A, then you just pop that in here, and everything goes through. So yeah, so this defines S inverse M as an S inverse A module. And I think we'll call it there, and we'll discuss the functorial properties of localization in the next half of this lecture.